All right, hi everyone, and welcome to the MIT Robotics Seminar. It's a great pleasure for me to introduce today's speaker, Professor Andrew Davison. Andrew is Professor of Robot Vision and is the Director of the Davison Robotics Lab at Imperial College London. His research interest, as you might know, is about simultaneous localization and mapping, as well as spatial intelligence for robotics. And Andrew's been really, a pioneer in robot perception and computer vision as well. His work includes many firsts. Just to recap my favorites, MonoSlam was the first work showing a working demonstration of a monocular SLAM back 2004. Then there was Kinect Fusion showing the first, demonstration, the first example of SLAM system, real-time SLAM system with RGBD cameras. Another favorite of mine is Semantic Fusion, which was showing the first real-time system doing metric semantic mapping in real time. And more recently is doing very cool work at the intersection between SLAM, Gaussian splatting, as well as feed-forward transformer models. And hopefully we're going to hear about that in his presentation. I think much more generally, I think Andy has been a thought leader in the community and has been guiding a lot of transition we have seen in the community from the traditional notion of SLAM to the frontiers of having robots that understand the environment more like humans, and a frontier of research that is calling spatial AI. It's now a new field of research in robotics. So of course his work has been broadly recognized, including, for example, a Best Paper award at TCCV 2016, Helmholtz Prize at ICCV 2021, as well as a very cool Best Demo Award last year at CVPR 2024. Was elected Fellow of the Royal Academy of Engineering in 2017, was a Fellow of the Royal Society in 2023, and finally he was a co-founder of the SLAM startup SLAMcore, which is another example of the effort he's putting in transition essentially perception technologies to the real world. So I'm very excited about this presentation. Let's welcome Andrew Davison.
Yeah, thank you very much, Luca, for the invitation. It's great to be here. And John here was just saying the last time I was speaking at MIT was in 2002, so too long ago. But it's great to be back. Apparently, the Stata didn't even exist then, I think. So again, anyway. So my talk's called Spatial AI, which, as Luca explained, is the sort of general term for what I'm interested in. And then towards the end, I'll talk a bit more about distributed computation, which is something I'm particularly excited about at the moment. But I think a lot of people are interested in building applications like these, so general purpose home robotics or things like wearable smart glasses. So these are devices which would either fully autonomously or in collaboration with a human hopefully really understand the scenes that are around them. So if we really want them to be able to do generally intelligent things, and my example for a robot is something like, clear up a messy kitchen after you've had dinner, or in the case of these glasses, really serve as a very general intelligent assistant that could really remember everything you've been doing in a day and the context and really give you advice and things like that. How are we going to enable that sort of situated AI? So which is not just the sort of AI which is guided by a prompt or an image, but is really knows about all the context of everything that's going on around it. So some questions about how to build that, and really kind of current one at the moment is an explicit representation of the world necessary for this general embodied AI? So you might hear a lot of people thinking it's not, and we're just going to solve things like this by kind of end-to-end learning of networks that go from kind of images to actions and things like that. I would be on the side of saying if you want a generally intelligent system like this, it should build a representation of the world around it. So a term you might hear a lot recently is a world model. That is the sort of idea of a machine learning understanding of the world around a system that allows it to plan and simulate and decide what to do next. So I agree that systems should build models of the world, but I think that's what we've always been interested in the sort of research I've been doing. And the big question is, what should that world model be? Should it be something like a relatively explicit map of the world, which has objects and features and physics and things that we can interpret and understand, or will it be just some very abstract set of vectors within a neural network? So my instinct is more towards the explicit there, and that will be revealed, although I think this is still a kind of very much ongoing debate in research. And so actually I think the best current systems for representing the world and enabling this kind of general embodied intelligence are very much a kind of interplay of learned and designed components. And I'll show you some systems we've built recently that have that character. So I've worked on visual SLAM now for 30 years, and those systems so there are visual SLAM capable systems that are now out there in real products, and these are in several areas. Some of these we would definitely call robots, things like robot vacuum cleaners. That's something I've worked on personally. Things like drones that can navigate around and use cameras to do localization mapping, and then also other devices, so smartphones, and then things like AR, VR headsets. So these are products that you can already buy. They do run visual SLAM, so they do generally sparse mapping and localization. So the key enabling thing that these products have is that they know where they are in space, and they do that by building a sparse map of the scene around them, so a set of landmark points. And that enables localization. It enables a little amount of scene understanding, but not very much. So if we want to step up towards these more generally intelligent products, we're going to need to understand more of the scene around those devices. So I call that capability of sort of generally understanding the scene around you in order to do intelligent things, spatial AI. And I've been using this term for a few years now, but it really seems to be catching on, and I meet a lot of people talking about spatial AI now. So my argument is not that spatial AI is a sort of level, it's a separate system that runs on top of SLAM, it's that SLAM is evolving into spatial AI. So we can see that as we've worked on SLAM systems over the last 20, 30 years, we've gradually added more capability into the SLAM system. So we've moved beyond just sparse feature maps and localization towards systems that can do dense mapping of scenes, and then increasingly also semantic understanding of scenes, but still within the constraints of what we call a SLAM system. So a SLAM system for me, it runs in real time. It runs hopefully with fairly reasonable low cost sensors and processors, and it runs on real platforms. It's robust in the real world. You can get it out there and actually test it. And even the way that SLAM research has been carried on in my labs and others is often marked by these sort of demo systems, the sort of things that Luca was mentioning were not just papers with dataset results, they were actually testable systems that you could often download and play with, and running in real time. That is the flavor I think that we need to stick with. So my argument is that SLAM has always been evolving into what we've always dreamed of, this kind of representation building system that builds us representations to enable embodied intelligence. So the general kind of thinking around a lot of this, my thoughts about it are actually, there's a kind of white paper, a discussion paper called Future Mapping the Computational Structure of Spatial AI Systems. And in fact, very much based on that, I've just recently contributed to the SLAM handbook, which will be coming out soon, which Luca and others have edited, but there's going to be a chapter in it really based around a lot of the things that I'm going to discuss here. So some of the hypotheses that I have, as I mentioned, is that spatial AI will be enabled by systems that build these representations of scenes that are, exactly what the representation will be. There's a lot of questions, but I think it may be closer to metric 3D geometry than a lot of people think, if it's going to be really generally useful and also efficient. And then also that there's a generality to spatial AI systems. So whether you're building the localization system for a drone or a home robot, maybe the systems will be quite similar, but with a few parameters that are different. So, some of the questions in general about spatial AI systems. So what are the best candidates for scene representations? what is the trade-off between bottom-up learned components that we can just run and expect to give us an output on every input piece of data like an image? Where does that meet some sort of iterative back-end that's going to optimize things? And then in particular, what computation patterns will enable the highest efficiency with future sensing and processing hardware? So how are we really going to take a demo system that might at the moment need a really powerful desktop PC to run? How are we going to pack that down into tiny embedded devices that will actually enable products? So I think the key to all of this is thinking about representations, thinking about patterns of storage and computation, and then eventually mapping those patterns down onto the actual hardware that will implement this. So I'll come back to this later, but I think that co-design of processors and the algorithms that run on them will be really important. Okay, so I'm going to show you a few examples of some of the systems we've done in the last 2 or 3 years, really, in our lab, and comment a little bit on where I think they are. So and the video will probably not work when I just click on it, but I think I can easily find it here. So first of all, this is a Gaussian splatting SLAM. So this is a paper that we published last year. This was the one that won Best Demo at CVPR 24. So it is a SLAM system that runs in real time based on Gaussian splatting, which you've probably heard of. It's a scene representation for computer graphics that represents scenes with many small colored blobs, little Gaussian blobs. So, Gaussian splatting, the original work was, you would train a Gaussian splatting representation from a set of posed images, and then you could render it efficiently from lots of different viewpoints. What we built was a SLAM system where the scene representation is a Gaussian splatting set of blobs, but we're going to train that in real time from a camera moving around, and we're simultaneously going to estimate the position of the camera, essentially we keep rendering from the Gaussian splatting model and then adjusting the parameters of the camera so that the rendering matches up with the image that we've just taken. So in terms of a scene representation for SLAM, this has some really nice properties. We can capture, incredible detail. We can even capture things like transparent objects. If you look closely, each one of these objects is made up of, hundreds or thousands of these tiny little blobs. This is showing a little bit more how the system works when it's first building a model. We just initialize loads of random Gaussians and then gradually optimize them so that the renderings are matched up. So something about this system is there's no sort of priors in this system. So it's really only feasting on photometric information. So the more views you capture from more different viewpoints, the better the reconstruction will be. There will be holes if there are things you haven't looked at. You're not going to reconstruct the back side of objects and things like that. But with enough data, this will converge to something really, really good. But you might say in a lot of applications in robotics, for instance, you're not going to always be able to move your camera all around all of the objects you want to, observe. I want to avoid an object or pick something up. I'm not going to exhaustively scan it first. So next up, I really apologize about these videos, but so there are some kind of systems that we actually did a little bit before Gaussian splatting SLAM, but I would say are kind of related in that we're using machine learning type of machinery as a map representation. So in IMAP, this was a system that we worked on shortly after NERF came out. So NERF is a paper that represents scenes with a single MLP neural network, where the structure of the network is such that you query it with a 3D point, and then the network will output properties of the scene at that point, so color and density. IMAP is a real-time SLAM system built on that concept. So as you move a camera around, you'll incrementally build this model of a scene. This had the nice properties of this. First of all, it's quite a small representation. So the network representing this room is only about 1 megabyte of weight. So it's really, really efficient. On the other hand, it's efficient in terms of memory, but it's relatively expensive in terms of computation. So you have to do kind of rendering from an MLP network in order to calculate the loss and update things is relatively expensive. And therefore, to make this run in real time, we had to take some steps like sampling rays rather than rendering the whole image. And so the model that it builds of a scene is, it's quite nice. It's not super high quality. It has very nice kind of smoothness and continuity though. So because it's generated from an MLP, it prefers sort of generating models of a scene that are smooth and coherent. So if you can think about it as it's compressed the input information into this relatively small neural network, and it's done that by finding areas of coherence. So in fact, that led us on to a follow-up paper called iLabel, where we showed that we could add an extra output channels to this network representing semantic classes in an open set manner, but where because the outputs for semantics were generated from the same network that's generating shape and color in this network here, these outputs inherit that kind of strong coherence. So that means we could label a scene with semantic properties with very, very few interactions. So in fact, these kind of points here are where we've clicked on the image very, very sparsely, and we're able to label the semantic properties just with very, very few interactive clicks because the network is generating a coherent scene anyway. So that was called iLabel. Some other nice things we did based on these sort of neural network-based scene models. We did some work on model fitting. So this would be a nice one to show you. I think I've got this one here. Yeah. So here we're showing if we build a kind of NeRF type model of a scene. So we do that by, we've just got an RGB camera here mounted on a robot arm. It scans this scene and gathers a set of images, and then it puts those into actually a system called Instant NGP, which is a very fast NeRF type of system. So Instant NGP generates a scene model with a density field and a color field that looks like this. So the density field is what we're interested in here. It's not perfect in many ways. So the white areas are high density and the black areas are low density. And you can see, especially on textureless surfaces, it has a hard time knowing that there's a surface here. But what it does capture very well is a lot of good details about the edges of objects. So if we then actually go on and we're trying to actually find specifically where objects are in this scene, we can fit 3D CAD models to this representation. So we've got our models of the objects that we expect to have, and then just using a simple optimization, we align them with the density fields generated from Instant NGP. And in fact, this works really, really well. So especially for small, tricky objects like screws and nuts here, we're able to estimate their positions to kind of millimeter accuracy, and it's only from color input from scanning this scene. So that kind of idea of object level representations, I think is very valuable, especially if you want to do robotic things like manipulation. So we have actually done quite a bit of work on using systems that can fit CAD models of objects. So if you really know which objects you're expecting to find in a scene, go and actually fit models of those objects, and then you can do some really nice manipulation, of quite complicated things. So those systems, so far, yeah, they're saying, well, maybe we do want to get to object level understanding of a scene, but the way we're going to do it, we'll first do a sort of very brute force reconstruction, Gaussian splatting or NeRF type thing, build the best model we can just from photometric information with no priors, and then go in and fit the objects and try and find where they are. But that's probably not the right way around to do it, because you've got this huge amount of work you have to do first, and then you only kind of do recognition at the end. So what if you bring that sort of, learned thing earlier on? So do more sort of recognition early, apply neural networks to images, and then do SLAM kind of on the outputs of those. So that's a kind of general approach that I would say we've been looking at quite a lot. So in particular, we've done this work where we're running normal prediction networks on images. So DSINE is a very nice piece of work from Guangbin Bei that was in my lab that can look at single images and predict normal fields. So there are all sorts of neural networks that can predict things from single images. So for instance, you can predict depth from a single image. People have tried to build that into SLAM systems, but it turns out to not work that well because depth is actually quite a hard thing to predict. So, I look at that floor over there. It doesn't have much texture. The neural network's very good at knowing that's a flat surface, but what it's not very good at is knowing, its exact, distance or height or orientation. There can easily be some systematic errors there. Whereas if we sort of back off a little bit and say, well, let's not predict full scene depth, but let's predict just the gradient of that. So let's predict normals, which are basically surface orientation. That's something that even a simple network like a CNN, which is really fast, is able to do very well and give you results like this. So, all these green pixels, so we've got a color coding of normals here. So all the green are kind of upward facing normals. So then we've built a SLAM system based on this. So Superprimitive, it actually uses the normal prediction network and then one other network. This one must be here somewhere. Is it this one? No, it's not that one. It's this one. So Superprimitive, we have input frames, and on every input frame, we run at the moment 2 separate neural networks, but I strongly believe these could be joined into one network. So first of all, we have a segmentation network. We're using here off-the-shelf the segment anything model, turns this image into object-like chunks. And actually, we don't mind if this is an over-segmentation. But for what we really care about is that each of these chunks is a coherent piece of geometry such that if we predict the normals within this chunk, we won't have any normal discontinuities, and then we can integrate up the normals here to give us a local shape. So if you know the gradient of the surface everywhere, you can integrate that up to get the shape. But of course, in integration, you have this unknown thing, which is the overall scale. So because we're only integrating up normals, for each of these chunks, we know its local shape, but we don't know its distance from the camera. So we don't know whether it's a small chunk that's close to a camera or a large chunk that's far away. But then we can bring in multi-view information. So now we have a second view from the camera that's moved a little bit in the future, and we compare each of these hypotheses of depth by reprojecting it into the other image and testing whether it's photoconsistent. And then when we do that with all of the chunks, we can actually build a good reconstruction just by basically moving these chunks around. So this actually now turns into a really general kind of object-based SLAM system. So here, for instance, is a little 3-view structure from motion example. So here, we've got 3 images taken from a camera that's moved a little bit, and then we're going to jointly optimize for the positions of the 3 cameras and then the depths of all of these chunks such that the depths are photoconsistent so that they project into similar things in the other views. And you can see that we get this very nice reconstruction. And then we can also build a full visual odometry system out of this. So here we're incrementally doing this in each key frame. We're doing building the superprimitives and then optimizing the positions of the superprimitives multi-view. So this is a quite general multi-view kind of object-level SLAM system that kind of works on anything. So this is quite surprising to me. So having worked in the past on object-based SLAM systems that made really specific assumptions about the kind of objects that would be present, now we have these bottom-up tools that can segment any image into reasonable chunks and then normal networks that can get their depth quite well. So this is giving us a nice reconstruction, which is very, very clean, but it's also, by default segmented into object-like chunks. So this could be a really nice representation for things in the future. So I'm going to show you one more thing here. So another system that we've built is called Como. So this is another system that uses a single frame neural network on every frame and then passes that over to a SLAM backend. But this network is doing something a bit different. it's not predicting depth for a single image, but it's predicting something called depth covariance. So for any pair of pixels in an image, it's telling us how related it thinks their depths should be. So if you two pixels that are nearby and in the same object, their depths should be highly similar and highly correlated. Two pixels that are on different objects will have uncorrelated depths. So that is in the form of a kind of Gaussian process model, which we can then easily combine with optimization tools. So what you see in this system is we have a set of basically control points. These red points here are the explicit state of this system, where we're explicitly sort of estimating the position of a set of 3D points that we think should be on the surface. But then via the depth covariance function, for each view, we can turn that into a full depth map. And then we basically optimize that so that the depth maps are consistent multi-view. So this is another system that works really quite nicely, and it works live. It's not doing the explicit kind of decomposition like Superprimitives, but it gives us quite a nice way of reconstructing scenes in real time. And then the last system I'll show you kind of in this theme is called Master Slam. So this one is work that we're just publishing this year. We're going to be demoing this at CVPR if you're there. So this is now using a stronger network than ever. So something that's quite interesting is I mentioned it's hard to predict depth from a single image, and therefore the approach we took was let's weaken that a bit then, let's predict a bit less. But then this work comes out, so Master is work from Naval Labs Europe, and they showed you could train a network that would take in pairs of images and then directly output 3D point clouds in a way that's really surprisingly good. So this is something that really surprised me. So trained on lots of data with ground truth 3D. So two images in and 3D point clouds out. So what we've done in Master Slam is built a SLAM system around that. I've got the video here. Let's just go back to the start. So there are some really nice properties of this. It's probably the most kind of robust, dense SLAM system that I've ever played with. So this works just from an ocular camera, and in fact the way we've run it here, we're just streaming live video frames from an iPhone to a PC. So the processing's done on a PC. Every pair of frames is kind of thrown into Master that gives us this local 3D reconstruction, and that's what this kind of colored stuff going on here is. These are the sort of local 3D point clouds. And then we have a SLAM pose graph built around that, which is optimizing all of these pairs of frames and making the 3D reconstructions match up. So in fact, we have to do that with a 7 degrees of freedom similarity pose graph because we don't know the scale of these point clouds. But we put that all together and we get this very, very robust SLAM system. So this is 4x, so you can see this. You know, this is somewhat sped up, but this does work pretty nicely in real time. So it builds a model which is, in the end, it's a massive cloud of points that are somehow all sort of mushed together. So it might still be a good question, is that a good long-term representation of a scene? But just as something that can crunch out and give you geometry really well. It's also very, very generalizable. And one of the really great properties is it works pretty well, Master, even if you don't know camera intrinsics. So for someone in SLAM and 3D geometry like me, this is sort of astounding that you don't actually need to know the focal length. And it can still give you a pretty good 3D cloud. It does actually work a bit better if you have it, if you do have geometry, if you do have that. But so, for instance, in this one, what we highlight is we're actually going to continuously change the zoom of the camera. So we're moving this iPhone around and we're kind of zooming in and out. We don't have any knowledge of what that zoom is. We're just taking the video sequence and we're feeding it into the into the network. So that means, for instance, you can run this on YouTube videos and it works pretty well. And we went a little bit viral on Twitter showing it was the opening scene of the Shawshank Redemption when there's this kind of flyover of the prison and stuff. You can get quite good reconstructions. Yeah, here's outdoor, the Royal Albert Hall in London. So yeah, strong prior being used here. Okay, so let's come back to the sort of overall discussion here. So yeah, we want to make spatial AI better. We're interested in making it really good and really efficient. And as I mentioned, I think we need to think about the sort of structures and how does everything relate to each other, and how we might lay that out on hardware. So I'm going to turn now to talk more about the kind of hardware side of that. So I first kind of got interested in this. I mean, partly, I was working on some real products. I'd worked on SLAM on robot vacuum cleaners, understood some of the things about wanting to run SLAM algorithms on, embedded boards that don't use much power and stuff. We had a project where we tried to sort of be a bit more systematic about investigating this, and kind of took a SLAM algorithm apart and looked at all the different parts of it and looked at how well they worked on, big desktop machine down to tiny embedded board. And, try to understand, in particular, how do we embrace parallelism in SLAM? How do we embrace, not moving data around too much? And through that work, got to know a bit more about how processors work and what might be happening to processors in the future. So clearly, for many years we worked on SLAM just with CPUs, and CPUs got faster every year, great. But CPUs are not getting faster anymore. They get too hot. You just can't run them any faster. So we have to embrace parallelism. That's the way to throw more compute at problems. We all know about GPUs. They enable massive parallelism, but a certain sort of parallelism where essentially it's this SIMT type of parallelism where a lot of cores are doing the same thing at the same time. And that has certain things it can do really, really well. But there are new sorts of processors, coming. So one prototype, well, this is actually a product, but there's a company in the UK called GraphCore that makes what they call a graph processor. They call it an IPU, an intelligence processing unit. But it basically has many processing tiles on a chip, so maybe more than 1,000. But each one of those can be running a separate program. So think of it like a tiny CPU. It has its own local memory right there on chip, so up to something like a megabyte per processing tile. It can do super, super fast local computation there. And then it has a kind of all-to-all interconnect structure so that all the tiles can do a little bit of work and then they can exchange information between themselves. So I think that's a sort of pattern of chip. Maybe it's a bit more brain-like. There's very much this kind of co-location of processing and memory. And so most of the work is done locally, and then you have some sort of exchange to keep things synchronized. That is potentially a really, really low power way of doing things. And I think we're going to see a lot more processors that are built in this kind of way. So I've been thinking a lot about, what kind of algorithms are suitable for that sort of processor. So those of us in SLAM know that, usually the framework where we design and understand SLAM algorithms are probabilistic graphical models, or specifically factor graphs. So we have the things we're interested in estimating. Here they're these blue variable nodes, and then we have information from sensors or constraints, which are represented as factors. So basically, to solve SLAM and spatial AI problems, we want to do inference on these factor graphs. And there are many good algorithms for doing that, but most of them are really designed for CPU type of things. You build a big matrix, you find the sparsity, you find an efficient way to invert it, that kind of thing. There's tons of good algorithms for doing that. But what if you're trying to do this on this much more distributed computer, which has many local processing sites? So there are algorithms that can do distributed inference on factor graphs. And especially I've got interested in Gaussian belief propagation, which is a really quite general algorithm, which in some ways goes to a limit of assuming how you can solve problems like this with no sort of global knowledge. Each node works in a completely independent way. So we've got this online article called a visual introduction to Gaussian belief propagation, which I can briefly show you, which kind of shows you some of the properties of this. So this is an article which is in HTML, which has lots of sort of built-in demos. So I'll just quickly show you a couple of the properties. So let's say we've got the simplest sort of problem that we could think of, which is trying to fit a kind of line to a set of height observations. So these red points here are observations, and we want to estimate the height of the surface at a regular series of positions. We build a factor graph which is something like this, where we have these constraints here that try to move the variables here to be close to the measurements, and they do that in a kind of interpolated way here. But we also have smoothness constraints, so we don't just want to pull the points directly to the data, we also want our whole line to be smooth. So this could be any sort of assumption that you have. So here we've got an example, we've got this set of observations, and this is where I'm going to try and fit the points. So I want to solve the factor graph. I can solve it by passing messages with Gaussian belief propagation. So here we're going to pass messages left to right across this graph, and you'll see the variables move as they receive the messages, and then show that as we pass messages all the way back. So because this is a factor graph with no cycles, when we just do that, pass messages all the way one way and all the way back, we actually get the perfect solution. So if I click toggle true marginals, that's calculated using a standard method. So let's just clear this and try it again. So let's put some more different data in here. What happens if we use a different message pattern? So what if we do synchronous message passing? So this might be the sort of thing you do on a graph core chip. So if you'd laid this factor graph out onto the chip, and every chip was doing locally calculating messages and then locally passing the messages, you can see that we can get to the same solution just by iterating that synchronous message passing. But even cooler is what if we try it again and just pass random messages? So now every time I click this button, one node is passing a message to one random neighbor. And if I iterate this enough, again, we still get to exactly the same solution. So this is a really kind of amazing property of this algorithm, that it can converge with completely kind of asynchronous, non-local computation. So that's a really simple 1D example, but we can generalize this a lot. So here's now a 2D example. So think of this as like a kind of 2D pose graph. We're going to solve it here by synchronous iterations, so pass messages a few times. So this is now a graph with cycles, and Gaussian belief propagation can still converge in that case. So this is very sort of promising in my opinion, and we've tried quite a few different things with it. So in 3D SLAM, we've tried implementing the classic vision optimization problem, which is bundle adjustment, which is saying I've got a set of cameras and a set of points, and I want to find the optimal estimates of the positions of the cameras and the points to minimize reprojection errors. You can solve that on a graph processor by basically laying out, I think it's this video, yeah. So you take the bundle adjustment graph, and you literally just lay it out on the tiles of your graph processor. So if you've got a small enough graph here, you can literally just lay down, one node of the graph onto one tile, and then you solve the algorithm by just iterating, passing messages around this graph. So we have kind of different cycles here where we pass messages between them. And then we need to do, quite a lot of iterations, but each iteration is so fast here that we showed we could solve, smaller bundle adjustment problems, extremely fast. So that work still hasn't been taken much further yet, but it's actually led me into something different, which I'm really interested in at the moment, which is especially when we see that this can work with, very, asynchronous operation, we can apply it to bigger problems. So what about multi-robot systems? So an example might be, a system of the future where there's, many different autonomous agents doing a job in something like a smart farm of the future. How are all those objects going to know their positions, for instance? Are they all going to need to talk to some kind of grand, overall cloud, like the future of a cloud maps system that's going to coordinate everything, or is there a way they could all estimate their locations in a distributed fashion? So we've got this work called Robot Web that basically looks into this problem. So this is a factor graph for multi-robot localization. So what's going on here, we've got 3 robots. So each one has a set of variables representing its positions at different points in time. So for this green robot here, it's got 6 variables representing estimates of its position at different times. And then the factors we have, first of all, it will have some local factors here in black, which might represent odometry. So some local estimate of its position gives a relative constraint on the position at time 1 and time 2. But then the robots also observe each other. So all these robots are all roaming around. When other robots are nearby, they observe the relative positions of the other robots. So those give these factors here, which join 2 variables from different robots at the same time. So at this time here, the red robot observed the yellow robot, the green robot. At this time here, they both observed each other. So these give us these constraints. So if we did have a full kind of cloud system and all the robots just uploaded all their measurements to the cloud would build this big factor graph, it would solve it, and it would send the positions back down. But instead, we can solve this problem locally. So what if the robots are just moving around and communicating peer-to-peer with no global centralization? Each robot can, it holds this part of the factor graph within a dotted line on its own processor and passes messages around this fragment within its own processor. But then when it needs to pass messages across the dotted lines, that requires communication. But the nice thing is this communication and message passing can happen asynchronously. So Robot 1, it has something like, we call it a robot web page, which is basically a representation of all of the latest outgoing messages which cross its dotted line, which it presents on something like a web page. And when any other robot comes near and manages to get into contact, which could be via Wi-Fi or some other communication technology, it reads that robot's web page and says, are there any messages for me? In this case, it would be these ones that go between green and blue. Read those and then incorporate those into its own factor graph here. And then that whole thing can work with completely distributed peer-to-peer communication. So the actual content of these robot web pages are actually just fairly small matrices that look like this. So they don't need that much data bandwidth. And we can also deal with complicated 3D states and things like this. I'll just show you a quick demo of this system, so I can actually run this here. So here we've got a simulation. I'll show you this case of 100 robots. So they're all running around. So maybe if I, sorry, there's a lot going on here. So let's turn that off and that off. So first of all, if I turn off measurements here, you see we've got 100 robots running around. And then in our simulation, for each robot, we've got an estimated location and a ground truth location. And you'll see that these kind of diverge away from each other if they're only using odometry to estimate their positions. But now let's turn on measurements. Where is it? So let's increase the sensor range a little bit. So now the robots will basically start observing each other. And this pattern of lines here shows the measurement pattern. So the sensors have a limited range, and robots will only measure each other when they get close enough. But now they're basically solving this really, really complicated factor graph problem in a purely distributed way. So each of these robots doesn't really need to know anything about anything else. It doesn't need to know how many robots are in the whole swarm or anything like that. It's just doing purely local computations, and we're able to get good localization. It's also very robust, so we can deal with robust factors here. So if I turn up this thing here, noise fraction, I'll say that now 30% of all measurements are just complete garbage, but we have kind of robust kernels operating within the message passing system. So all the blue lines here are basically rejected measurements, and the whole system stays accurate overall. Anyway, so that's something I'm very excited about at the moment.
Quick question.
Yeah.
I think in the Robot Web paper you assume range and bearing measurements between nodes.
Yeah.
Have you looked at all between having just range measurements?
Not explicitly. So we have range and bearing with changeable covariance on each one of them. I would really like to investigate that property because in your underwater systems I would assume that's what you've got. We can also do auto calibration within this. So if each robot also has some unknown calibration parameters, we can do that. But maybe because there's not much time, I'll just show you this work. So we realized that once we could solve these multi-robot estimation problems in a distributed way with GBP, actually what has a really, really similar computational structure are multi-robot planning problems. So what if you wanted to plan for a lot of robots to, travel through a junction like this? I've got to find this video, yeah. Here it is. Okay, so when we do local planning, so let's say here we've got two robots that are trying to cross this junction. So now each of these robots, this is its current position, and then these are its planned future positions. Now there are constraints between every two consecutive, parts of the plan based on dynamics. So this position and this position have to be related by the possible dynamics of the robot. If there's no other problem or collision, they'll just move forward as fast as they can. But if the robots start to get close to each other, we also define constraints between time equivalent poses of this robot. So this robot at time t plus 10 cannot be too close to this robot at time t plus 10. So think of it as like we add a spring between those two robots. So these are all least squares constraints on the dynamics and on the collisions. And it turns out, therefore, to be absolutely identical to the kind of multiple Gaussian problem that we were doing with localization. So we're solving a distributed least squares problem, and therefore we're going to do it with the same kind of robot web style asynchronous message passing. And that, with two robots, okay, no problem. So this is what happens. They each make a kind of small adjustment. So you can make a small early adjustment to your velocity and you miss each other. But as we add more robots, you can think of, essentially what needs to happen is a kind of negotiation. So because each little adjustment that one robot makes may put it in the path of someone else. So you do need to solve this kind of full joint planning problem. But to show that we can solve that with distributed computation, I think is really interesting. So this is a sort of classic problem that people look at in these sort of multi-robot planning questions. This is a really difficult situation where you've got to cross this circle with lots of barriers. But you can see nice things like little emergent kind of corridors where robots kind of follow each other and that kind of thing. Let me just show you this bit. Here's a more complicated one where the robots are not just trying to move straight on, but they're actually going to try and turn. So some of them are driving straight on, some of them are turning left, some of them are turning right. So yeah, I guess this is the exciting possible future of autonomous cars where you can fit so much more traffic onto the road. Okay, so the last thing I'll talk about, let's just go to this. So I've talked about neural networks and factor graphs. I've said that we're going to have to put learned components in together with estimation if we're going to build powerful spatial AI systems. But I'm really unsatisfied with the way that works at the moment. So you have the output from a neural network that's predicting normals, or it's like master or something, and then you're going to try and incorporate that into a SLAM system. And that's unsatisfactory in several ways. One is that we don't generally understand the uncertainty of what's coming out of the neural network, and therefore modeling that uncertainty in the factor graph is hard. Another real problem is these neural networks are generally, baked and fixed. They can't kind of continually learn. So what we would really like is is a network that gets better and better over time and learns from what it's actually observing in the scene that it's in. So we've got this idea of actually kind of reinventing a bit the way that we might design a neural network to say, what if we actually put learnable components into factor graphs? So we call this GBP learning. So here's an example of a sort of convolutional structure. So, a normal convolutional neural network, so it has neurons and it has weights. So the weights are the things that we're trying to learn. The neurons are the things that kind of put them all together. It's really quite similar to variables and factors. So variables are things that we're trying to estimate. Factors are the things that kind of join them together. And we can put nonlinearities into those factors as well. So the concept here is that, so here, for instance, we're trying to, do some recognition of digits. We have variables that are kind of reading the values of the pixels, but then we have some extra variables in our system here which are playing the roles of learnable weights, but we're going to find the values of these things just by running factor graph inference, and we're going to be doing it by GBP message passing around these graphs. So, admittedly, this is very preliminary. We've got a paper at ICML about this. The results so far are quite simple, I would say. But is there a way to make proper kind of Bayesian learning that could be properly integrated with all our normal probabilistic machinery and work continuously? So, so continual learning is something I often think about. Neural networks are not good at learning over time, but we know how to solve that problem in SLAM. We've been working on that for years. We know that probability is the right way to judge how much is the weight of a new piece of data I've just captured. How do I weigh that against all the information I've already got in a map, for instance? And because we're doing it probabilistically, that works well. We know how to properly weight the old and the new. So why shouldn't we do machine learning in the same way? And there's lots of people talking about Bayesian machine learning, but I think this is a proposal for a way to do that, which is actually quite computationally tractable. So yeah, definitely also on ongoing work we're going to keep looking at. Okay, so just to conclude, spatial AI research, I think we're going to be doing it for a long time yet. Some of the most important issues are, what are the right long-term scene representations that will enable really general intelligence, how implicit or explicit they will be. So definitely spatial AI will have significant learned components as well as estimation structures, but what's the right way to do that? How should we balance them? And yeah, we're just exploring many possibilities at the moment, I think. And then crucial, I think, are the computational patterns of the representations and algorithms that we use. Can we actually eventually be co-designing those together with the processors that they will actually run on to give us the best kind of performance and efficiency possible? Okay, thank you.
Thanks, Andrew. This is great. So we have time for maybe a few questions. Let's see.
So the GBP learning, how similar or different is it from graph neural networks?
I mean, probably quite related. Definitely in the sense that we're going to have networks that pass messages around graphs. Different in the sense that the messages that we pass here are kind of means and covariances. They're parameters of Gaussian distributions. These are also kind of completely directionless. So maybe that's also the case with graph neural networks. But I think there's a lot of relation, and this general question of networks that are not just sort of feed forward somehow, but are much more general sort of loopy graphs that you pass information around, I think will be something big for the future. And maybe the reason that we're so focused on some particular structures of neural networks at the moment is NVIDIA. They're completely dominant. They have one way of doing things. The only interesting networks at the moment are ones that work on NVIDIA, but that's just a passing phase. We'll get through that. We'll look back and we'll think, wow, can you imagine that we needed a data center the size of a warehouse to train a model? That's completely ridiculous. There'll be much more kind of clever, efficient things going on.
You showed a bundle adjustment problem and put it on a IPU,
Yeah.
just like a graph processor. Is there do you have to take some care on how you put those factors and nodes on the IPU?
Yeah. So yeah, so the reason I mentioned we were doing quite small bundle adjustment problems is that's the obvious thing. So so specifically on the IPU, the GraphCore IPU, you have to pre-compile the kind of communication pattern. So at compile time, you set what the pattern of communication between the nodes is going to be, and then also so in fact the IPU, it has just over 1,000 cores, and it has 6 threads per tile, I think. So what you can trivially do, if you've got a graph with up to like 6,000 nodes, you just can trivially lay it down. Once you've got more nodes than that, then you've got to solve some harder problems, and especially if you want to deal with changing graphs, which of course is what we normally have, what we have all the time in SLAM. These are not static graphs; they're changing all the time. So we've done some work on that, and I think the route forward is so you're going to have to give up a little bit on just this pure, geographical laying down of your graph onto the tiles. You're going to have to accept that you're going to have to move things around sometimes, and then maybe give up some of the compute capacity of the tiles to act as more like routing tables and DNSs or something like that. So maybe you don't directly pass the message from one tile to the other. You pass your message up to a routing node, and then that passes it back to the right place. My sort of hope is that you could sacrifice a relatively small amount of pure performance to get incredibly much more kind of flexibility and generality. And anyway, but we haven't had the chance to take that much further yet.
Have you looked into how your SLAM and spatial AI frameworks might work in a dynamic environment when your objects are moving?
I mean, bits and pieces of work on that over the years, but must admit I've mainly focused on the static case, and I generally think that we can map static things well. We can identify moving things, and probably we should treat those quite differently often. I mean, there's only certain things that move in scenes. It's people and things that people move, and then maybe in specific cases, cars and stuff like that. We've got good models of people and cars and stuff like that. So I'm always a little suspicious of why would we want to build really general dynamic SLAM algorithms. But yeah. All right, fair enough. Yeah. Yeah.
I have a related question, for when using foundation models for the front end, for example, for master SLAM, you know that these will have limitations. For example, deformable dynamic things, one issue. The other one is high distortion, maybe fisheye lenses and so on. How would you approach that? We just have, as roboticists and computer vision people, do we have to just wait for the next foundation model? What is the approach there?
I mean, it's true in general, we're in a bit of a tricky position there because in our lab, definitely we don't have the resources or the expertise to train those things ourselves. We'll use the ones that come out. But yeah, I'm always a bit wary about these big black box things that I don't really understand. I haven't built, and I don't know exactly how they work. I don't really know the answer to that. So you can either not use them and only use components that you really trust and you really understand, or wait or come up with clever ways to sort of adapt. I guess if you had fisheye images, you could sort of undistort them to perspective views and send those in, but that's probably the sort of thing we would normally do. but yeah, it's a funny time actually, because we shouldn't just ignore that stuff. We should try and make the most of it, I think. But yeah.
Final question. Maybe I have a more general question, which is related to the previous one about inductive biases. I think a lot of your first part of the presentation was about saying was about this tension between model-based and using priors instead. I mean, my question is, how do you explain the fact that that maybe this foundation model, master, duster, and so on are getting away without this? It seems that even having 2-view geometry priors is not really helping, for those. What's your take on that? Do we need those at the end? Do we need geometric priors at the end, or biases in this learning, or we can get away without them?
So of course, these systems work because they've been trained on a lot of data where those biases are present. Is that what you mean? They've seen loads of rooms with right-angle corners and flat walls and that kind of thing.
But also just 2-view geometry, right? So there is not much enforcing epipolar constraints on these models, right? So are we going to benefit by including this kind of geometric biases, or we can get away just with another large data set here?
Yeah, I guess all that stuff is implicit in the training data, isn't it? That they are all kind of ground truth camera positions and known geometry. So it seems that the transformer has just learned epipolar geometry somehow. But yeah, I don't know. A few years ago, I would have said, don't learn something that you already know, like 3D geometry. But then, yeah, the fact that they can take that relatively complicated stuff and just boil it down into this, big but in the end computationally simple thing. Very sort of uniform computation. Probably, I don't know. The question of efficiency is also a hard one, because also you start to think, big networks are expensive, but they do actually run pretty fast in the end. Okay, on big GPUs, probably bigger than we would eventually want to use. But yeah, no, I'm probably as confused as everyone on the whole about a lot of this stuff. It's I'm continually surprised by what is possible. So
definitely interesting times. Yeah.
Yeah.
Thank you so much, Andy. Thank you so much.